Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru, so I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bay. Then before that, bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is automatic transmission controls and testing. So in this, we're not talking about the gear sets and the bands and the clutches and all that. We're talking more about the external or the electronic controls, how we can test them, and a few different scanner functions that we can do with these in regards to testing and resetting and things like that on modern automatic transmissions. So first off, let's go through a little history lesson. Let's see how things have changed in the last 30 or so years. Because yes, this is a 1991 transmission right here, so that's 31 years old this year. Go figure that. But I decided to use a Camaro right up through, and then we're going to show multiple different transmissions and how they've changed. So back then in 1991, we had this 4L60, and a lot of parts, a lot of components, not a lot of electronics though. A lot of it was vacuum operated, pressure operated. So really, all we had for electronics was a speed sensor, a temperature sensor for the fluid, torque converter, clutch solenoid, and a switch that would tell it when it's in fourth gear. And that was pretty much all we had for electronics back then. Fairly simple, mechanically complex, but electrically simple. 10 years further down the road, we get to 2001, which is still 21 years ago. Even more electronics starting to show up. Speed sensor, temp sensor, torque converter, clutch solenoid, shift solenoids now, pressure control solenoid, and now we start having diagnostic trouble codes as well. So 25 possible DTCs back then, 20 years ago. Move up to about 11 years ago. Notice how we've now started gaining more gears in there. So it's a 6-speed now. It's a 2011 6L50. So that's 6 speeds. So there's kind of a big, maybe 15 years ago, a big explosion of manufacturers really starting to add 6 speeds, 8 speeds, 10 speeds now, even more automatic transmissions just to give them that finer control. And then we have the CVTs, which really don't have any gear ratios at all, but that's not what this class is about. So on the 6-speed, though, we have even more electronics. So we have 2 speed sensors now, input and output. Still have the temp sensor, still have the torque converter, clutch solenoid, shift solenoids, pressure control solenoids, which there are 5 of them, transmission fluid pressure switches, which there are 4 of them, an internal mode switch, which is like the Prindle switch, tells it when I'm in park, reverse, neutral, drive, and then 80 possible DTCs. So we went from 35 to 80 over those 10 years. And then if we go to a 1-year-old transmission, 2021, 10 speed, notice how we have gotten up to 10 speeds now. We have the input and output speed sensor the last one had, but now we also have 2 intermediate speed sensors as well for other speed sensor reading. Still have the temp sensor, transmission range sensors in there, and 9 transmission control solenoid valves. And we have 107 possible DTCs inside the TCM on this vehicle. So that is the most electrically complex. Sure, it's pretty mechanically complex in there too. We're really only looking at the valve body and electronics right here, but and then there's a separate pump as well. So the valve bodies are getting a lot more electrically complex as well. So let's talk about first, how do we get this thing in gear, so to speak, with gear selection? We'll start a little ways ago, probably back in that 20-30 year range, and we have the cable gear shift. So this one's on a Subaru. A lot of manufacturers use very similar type technology back then. We got a cable that mounts to this shaft here. We got this, arm. Cable mounts there. And then this actually goes into the transmission. That's the manual valve to allow it to kind of move things around inside the valve body. And then attached to this, or kind of riding on the back end of this, is the switch. So this is what we call an inhibitor switch. Could call it a Prindle switch, or the gear selector switch. Inside, it's just a bunch of mechanical switches, so it makes physical contact at certain points along the way. So a simple rotary type switch. Now, how we test for this is we check for continuity between the pins. We got in, we got out. We check for continuity in between, and we make sure everything's getting through. If it doesn't get through in the right gear range, then we know we have an opening. Also note, proper alignment in this case is key. Notice how the bolt holes are all along here, so it has some adjustment to compensate for maybe wear on the vehicle and the cable. But if it does get misaligned at some point, the vehicle might not start. This is a fairly common problem back then. Was the vehicle won't start, and then you come to find out, well, the switch kind of loosened itself up, and it rotated away a little bit, rotated backwards. So now when the rod is in park, the parking pawl is in place, and the manual valve is in park, the switch is not. So if the switch is not all the way back where it needs to be, then we don't make that circuit for the inhibitor circuit, and then the vehicle wouldn't start. So it's pretty simple to do. You just kind of rotate it. There's a little pin you put through it, aligns it properly, and then you're good to go. And then we get even more further along the line on more advanced transmissions. Some of the modern switches are actually internal in the valve body. Actually, a lot of them are at this point. So here's an example of a wiring diagram on that old style manual switch that has these connectors in it. We see it really has 3 sets of switches. This one goes out to the starting and charging system. That's my inhibitor part of the switch. So you notice it only makes contact in park or neutral. Reverse and drive aren't even wired. So it's hardwired connection. So if it's in park, sends a signal out. If it's in neutral, sends a signal out. Otherwise, it does not. That's what allows the vehicle to start. On this one, this switch goes to the exterior light system, and that's on the second one down, which would be reverse. So comes in here, exterior lights. And once it makes contact here in reverse, turns on the reverse lights. Very simple system. And then we have the actual gear indicator that each individual switch has an individual wire that goes back to the TCM. Back then, wasn't a whole lot of computer connectivity. It was just really a hardwired switches and relays and just a straight wire back to the computer. So that's all it was back then. So all I have to do is check for continuity. There's ground. There's my signal wire. Do I have continuity between ground and signal when I'm in park? Yes or no? And then kind of adjust it as you go. And if it doesn't work, then you know the switch is bad. If it does work, then you know maybe it was misaligned. That sort of thing. So that's where we're coming from. And then you get a little bit more advanced. They still use it because it would work. But then we get a little more advanced. We want maybe a sport mode. So a lot of vehicles have sport mode or sport gear shift, or what do you want to call it. Oftentimes, in order to engage that on the shifter itself, you put it into a separate gate on the side, and it has an up and down. So in this case, that's what this vehicle has. So a sport shift switch tells the computer when it is in that sport mode, because you can just flip it over to that sport mode and it will be in sport mode by itself, which changes the shift patterns, holds the gears a little longer, allows you to accelerate more rapidly or aggressively, depending on how you want to call it. And then if I want to manually shift the gears, plus or minus, there's just a separate switch for that. So if I go up, it hits a switch, manually, hits a little read switch, tells it, okay, I want to go up, hits another switch going the way down, tells it I want to go down. Once again, pretty simplistic system. It's just a bunch of wires and switches. Check for continuity, and that's actually in the select lever itself. So alternatively, though, newer cars than this, newer systems, you can have the steering wheel paddles or the switches on the back of the steering wheel, on the front of the steering wheel. In most cases, at that point, when we have our shifters up on the steering wheel, oftentimes it's going to be over a bus, a data bus. So usually they use LIN. So it's a 12-volt square wave data bus you would see. If you want more information on LIN, we have a computer data bus testing course. But that's oftentimes what you're going to see out of the steering wheel is going to be a bus situation. So you won't have all this wiring. You'll have just a wire or two coming out of there, and it's good to go. And then we have this this guy right here. So this depending on who you talk to, can be a little polarizing as to why they do this. I kind of think having a large round knob next to another large round knob for the volume and another large round knob for the blower could get a little confusing if I'm just trying to feel around and not take my eyes off the road. But hey, I'm not an engineer. I say that all the time. So some cars use it down kind of in the middle, which makes it a little less confusing that way. But you will find this most times on FCA vehicles, but other vehicles do use this as well. And this is not hardwired. This is all digital. It's a digital rotary encoder. So it sends all data over the data lines. All the communications over the network, you're going to use the scan tool to diagnose it. Now, you could check the CAN bus because it goes over a CAN bus and make sure you're getting signals. Signals are changing when you're flipping the switch. I guess you could do that and make sure the data packets look okay. But you won't know what the signal is sending. So if it has corrupt data, you wouldn't know. But you could tell on the scan tool. So really, you can check the harness, make sure the signal's making it where it needs to go. If the scan tool says that it doesn't see the switch, it's just like I said, it's a rotary encoder. We could spin it. The only real physical feedback you get is for the driver to understand that they're shifting. It really doesn't necessarily need that in order to operate, but you'll feel it kind of go into the gear it needs to go. Once again, using a scan tool. So this is the wiring diagram from that. So it's an electronic shift module right there. And then it goes to the TCM over a data bus. So it's CAN bus. And then we also have another CAN bus that goes out to the vehicle, computer data lines. So that is to send information to other modules, like the ECM might need it, the analog brakes might need it, need to know what gear we're commanding. So it sends that out. It's got a ground, it's got a power. Not a lot else going on. Power, ground, and 2 buses. So 6 wires total. All right, so now let's talk about sensors. First sensors, temp sensor. So we deal with a lot of different temp sensors on a car. In this case, it's a negative coefficient thermistor most of the time. As the temperature increases, the voltage decreases. We're going to test for voltage and resistance. Is the only really the 2 things we can do. Sometimes they are just buried in the valve body and you really can't get to them. Other times they're separate and easier to access. In the case that they are in the valve body, they can be difficult to get to. And I really need that for proper operation on the vehicle. So here's an example on that 01 Camaro. The transmission fluid temperature sensor is a 2-wire thermistor. As the transmission temp increases, thermistor resistance and signal voltage decrease. As temp goes up, voltage goes down. This is an interesting note here, though. Cold trans, voltage is sent through high resistance circuit in the PCM. On a warm trans, voltage is sent through a low resistance circuit in the PCM. This dual circuit improves the TFT accuracy over all temp ranges. PCM uses TFT signal to determine shift patterns, engage or disengage torque converter clutch, and determine hot mode operation. So that comes into play. The temp sensor, especially, it's top of my mind because recently it was very cold here, below 0, and that's Fahrenheit, below 0 Fahrenheit. And when you start your car and you drive it, it is cold. The car, all the fluids are cold. It takes a while, even if you leave it idling in the driveway for a little bit to warm up. That transmission really isn't warming up all that fast. So go driving down the road and you notice, okay, well, it's not shifting into 4th gear, or torque converter is not locking up or whatever. My vehicle, I'm just driving 30 miles an hour and I'm stuck at 2,000 RPM, or I have a high idle of 1,500, even though it's been warm for a while. It's just because that the PCM uses the signal to determine shift patterns and engagement or disengagement of the torque converter. Once it finally warmed up and the fluid was warmed up to a good temperature, then normal shifting resumed. So you could get a customer complaint if they've never driven this car in the cold and it gets cold and all of a sudden it's like, oh man, this thing shifts like garbage. That could very well be the problem. It could just be that it's cold out. And when it's cold, depending on what the fluid temperature is, the computer adjusts accordingly. Now back to that other point of the high resistance and the low resistance circuit. Look at this chart. So this is off that same Camaro. And you see my Fahrenheit, my Celsius. Minimum sensor resistance at that given temperature, nominal resistance and maximum resistance. And then you see my voltage. Well, you'll notice once I get to a little over 104, somewhere between 104 and 122, because it doesn't delineate it for us, but it goes from that high resistance to the low resistance. So if I were to say measure 3.45 volts, or let's say 3.01 volts, that's even 3.01 volts. So it could be 50 degrees Fahrenheit, or it could be somewhere between 122 and 140 Fahrenheit. So I would kind of have to use you can use the resistance numbers, of course, to check and verify, where you're supposed to be. But it could get confusing if you didn't realize that it's supposed to change over here about halfway down the chart. If you didn't know it's supposed to change over there, you might get a little confused. Or like at 1.10 volts, it's 104, and then 1.15 is 230. So if it's like 235, or is it 104? Right. So it could get a little confusing if you didn't know that it had that change over there. So it's always a good idea when we're testing these things to check and see if the manufacturer has any notes like that. And that note we saw was right out of the guided component test that's inside the Snap-on scan tool. Now let's talk about speed sensors. Now, speed sensors are a Hall effect sensor, generally speaking. Generates a magnetic field when that magnetic field is disrupted by whatever it is monitoring. So maybe it's a drum, or maybe it's a wheel on the shaft. It's going to generate a signal. So it either generates an AC wave or it'll generate a square wave, depending on how it's set up and whether it's analog or digital. Reads input and or output shaft speed or intermediate as well. We saw on that 10 speed, it had 2 intermediate speed sensors as well. And how we're going to check this is we're going to test for voltage resistance. There could be a signature test in there. Sometimes it's part of the valve body, as we'll see in a minute. Other times when it's like this and it looks just like a cam sensor, just one bolt on the outside of the case. Can be difficult to access if it's part of the valve body, or if it's in a weird spot on top of the transmission, might not be able to get to it either. But it is fairly simple to test. So here's just an example on a 09 Subaru with a 5-speed auto. Has 2 speed sensors. So turbine speed sensor 1 measures trans input shaft speed and torque converter speed. And then speed sensor 2 measures transmission speed. The location of them is driver's side of transmission near the middle for the sensor 1. Sensor 2, though, is in the valve body, right? So if I have a problem with sensor 2, I need to take the valve body down. So here's where I would test it at the sensor on the external one, and then on the internal one, I would test it at the actual pin for the transmission. And then all we have to do to test it, it's a DC voltage test, and we hook up to the speed sensor positive and black to a known good ground. With the vehicle stopped, I should see 0 volts AC, and then vehicle stopped us at least 12 miles an hour or more than 1 volt AC. So I'm going 1.2 volts AC right now. It's just giving me a simple meter. Not really a graph or a scope in this case. It's just pulling up the digital meter, reading volts AC RMS. So that's your average volts AC. And then remember how I said they could be internal? Well, in this case, this is on one of those GM transmissions we looked at earlier. And there's my input and there's my output speed sensors. They all share a common harness. And then the connector's over here. And you see it bolts to the top of the valve body. So in order to access this, I would have to pull this valve body out. And I don't really want to do that. Because they're just on top, and above that is all the gearing and such. And so it's a little easier to read, I guess, and protects them more. And you see it also plugs right into the module. The module is kind of all a self-contained unit with the valve body in this case. So you may not be able to test that without taking it.
So oftentimes in cases like this, sometimes the scan tool is the best way to test it. It just kind of depends on how the manufacturer has it set up. If I can check the harness and I can check the wiring easy enough, then I would prefer to do it that way. Maybe the scanner points me in the direction, but I would still prefer to verify electrically that it's working. Now let's talk solenoids. So we have a couple different types of solenoids, and we've done solenoids in class a few times, but there's two different types that we're going to see in the transmission. It's going to be on-off solenoid, which is a simple on-off operation. It's either open or it's closed. Computer controls the ground side or the power side, depending on how it's wired. And it's just an open and closed function, like I said. Sometimes it is part of the valve body and I can't get to it, or I can't get it separate. It's all kind of self-contained. Or it could be separate. It could be in the back of the throttle body or on the side and easy enough to access. Sometimes it can be difficult to access if it is part of the valve. There's an example on an 06 Subaru with a 4-speed. And this uses all on-off solenoids in order to shift the transmission. So it has 2 shift solenoids. And it has different application charts. So if they're both on, we're in first gear. If solenoid 1 is off and solenoid 2 is on, I'm in second gear. If both are off, I'm in third gear. And then if 4th is on and 2 is off, or 1 is off, 2 is on. 1 is on, 2 is off. I'm in 4th gear. It's easy enough to check when I connect it. It's just right at the transmission connector, right at the top on the bell housing. So shift solenoids 1 and 2 are on-off type solenoids. They're power side switched by the TCM and grounded through the trans housing. So knowing that, I can just check it on the power side. This tells us to road test the vehicle. When the solenoid is turned on, the meter reading should be battery positive. When the solenoid is off, meter reading should be less than 1 volt. Refer to shift solenoid apply chart for proper solenoid switching in each gear. So I should see on, off, off, on. You could also turn them on and off with the scan tool a lot of times too. On most vehicles, there's going to be an output control and on-off where I can turn that solenoid on, turn this on. Then we have pulse width modulated solenoids. So those are still kind of an on-off, but it's as a percentage. So computer controls the power or the ground side once again, depending on how it's set up. And it's an open close percentage. So if I'm at a 60% duty, that means it's on 60% of the time, it's off 40% of the time. So it just switches it on and off real quick. So it's kind of an open close, or it holds it open a certain amount, depending on how much current flows through there. Once again, sometimes part of the valve body, and when it is, it can be difficult to access. So we look at this 14 Ford Explorer on the torque converter clutch in this case, on a 6-speed transmission. Torque converter clutch solenoid is an integral part of the solenoid body, and being so, it is not available as a separate unit in this case, part of the valve body. DCC solenoid is both power side and ground side controlled by PCM or TCM on some vehicles. PCM or TCM controls common solenoid power used by all solenoids in order to cut power in case of a circuit fault. Solenoid duty cycle is controlled on the ground side to allow for smooth torque converter clutch application. The TCM controls the torque converter lockup by varying the amount of current applied to the TCC solenoid. When no current is applied to the solenoid, the TCC is fully released. When maximum current is applied, the TCC is fully applied. So this allows us to ramp up the amount of current going in there, so I don't have just a quick on and off, lock on, lock off. Best test location is at the 20-pin connector on the transmission, and it is located inside the transmission pan in the solenoid body. Just the connector views over here. And then here's a test, right? So a duty cycle test is going to give us a test and duty cycle. So 0%, 100%, starts at 40% in this case, works its way up to about 50, 60%, and then it's about 75%. Road test vehicle, observe the duty cycle percent while driving. PCM may command the TCC on in 2nd through 6th gears. At cruise with engine operating at normal temperature, duty cycle should begin to show percent increase as converter clutch applies. Converter is locked when at least 65%. So we're at about 75%. That means it's locked. Now I could also, alternatively to driving the vehicle, there are functional tests for that as well, on-off functional tests. So I set my pulse width on my torque converter clutch solenoid, and I should be able to watch it and mirror it as I go. If I hit 60%, I should see 60% too. That's how we can tell it'll work. And then on this vehicle, the 2011 Camaro, this transmission uses 2 on-off type solenoids and 6 pulse width modulated solenoids. So it uses both types of solenoids for pressure control on them. So working in combination, these solenoids control pressure to apply the transmission clutches, as well as control torque converter clutch operation and basic transmission line pressure. These are also not serviceable separately from the TCM. The entire assembly is called the Transmission Electronic Hydraulic Control Unit. The scanner is used to view their state. Scanner data displays the hydraulic state of the solenoids, not the electrical state. So it'll say whether or not it's flowing. It doesn't say whether or not it's electrically okay. The two on-off shift solenoids allow oil to flow through to move the appropriate clutch select valve when on hydraulically. Clutch pressure control solenoids control pressure at each clutch. Chart that follows shows the pressure control solenoid state as NH or NL, which is normally high or normally low. An NH solenoid allows pressure to travel to a clutch when the solenoid is turned off, whereas an NL solenoid prevents pressure from getting to a clutch when the solenoid is turned off. The shift solenoid states are shown as normally closed. These solenoids allow oil to pass through them when turned on and block flow through them when turned off. So we can see the chart right here as to what's going on. Also says you can use a pressure transducer or a pressure tester in order to test it. So 0 to 500 psi pressure gauge or a transducer. And then you can use the scanner to function up and down through the different pressure increments. And if we look down here, if I set it at a 200, then we see 100 to 130 psi is what we should see, 600, 220 to 250, and so on and so forth. Now here's a note, and this is pretty common nowadays. All the pressure controlled solenoids are programmed by the manufacturer to operate correctly together with the vehicle that the transmission is installed into. After being programmed to operate within a general set of parameters closely matching the assigned vehicle application the transmission was designed to operate with, the transmission needs to be operated through a number of shift cycles in order for the TCM to make the necessary pressure adjustments required for smooth and efficient shifting. So it has a relearn process or an adaptive process, or you may have heard it called an adaptation on this. So here's a couple examples of that. So on a 2014 Dodge, why would we need to do an adaptation, or what adaptations do we have on there? To equalize tolerances and wear, an automatic adaptation takes place for shift time, clutch filling time, clutch filling pressure, torque converter lockup control, and adaptation data may be stored permanently and to some extent can be diagnosed. There's also a driving style adaptation on this vehicle. The shift point is modified in steps based on the information from the inputs. The control module looks at inputs such as vehicle acceleration and deceleration, which is calculated by the TCM, rate of change, as well as the position of the throttle pedal, fuel injection information from the PCM, lateral acceleration, which is calculated by the TCM, gear change frequency, or how often the shift occurs. Based on how aggressive the driver is, the TCM moves up the shift so that the present gear is held a little longer before the next upshift. If the driving style is still aggressive, the shift point is modified up to 10 steps. If the driving returns to normal, then the shift point modification also returns to the base position. This adaptation has no memory, so it's not going to stay this way over a long period of time. The adaptation to driving style is nothing more than a shift point modification meant to assist an aggressive driver. The shift points are adjusted for the moment and return to base position as soon as the inputs are controlled in a more normal manner. So if you really get your foot in it, it'll adjust. Otherwise, it'll act as it's supposed to. Then here's another example on that 2011 Camaro. Service fast learn adapt. That's a procedure for a 6-speed automatic transmission in which a series of tests are run to allow the transmission control module to learn individual clutch characteristics. Once the clutch data is learned, Service fast learn adapts translates it into adaptive data cells, which the TCM uses for clutch control during shifts. Scan 2 provides initiation of the Service fast learn adapts procedure, and this procedure is to be used following transmission repair. So oftentimes when I do an internal service or overhaul, valve body repair or replacement, control solenoid valve assembly replacement, TCM software calibration update, or any service in response to a shift quality concern, this needs to be done. All right, so there's a certain number of parameters that need to be met. And once again, you drive a vehicle under certain conditions and it learns as it goes. So let's look at a couple other things that we can do with our scan tool. All right, so in this case, for this section, Going live on the tool here. We have a 2014 Ford F-250 diesel. So first off, let's just say we have a problem with shifting quality, or maybe we suspect it's a solenoid or something like that. Maybe we have a code for it, maybe we don't. But we want to test that solenoid. So if I have a tool with a scope, a snap-on tool with a scope, it's going to have guided component testing. We go into guided component test. I should back up a little bit. Let's go into guided component test, and then we'll choose our transmission system. And it is a torque shift 6. And then we can see all the different things on this transmission that we can test. But in this case, I want to look at these shift solenoids. Go to information. Torque shift 6 transmission may also be referred to as a 6R140. This is a 6-speed electronically controlled transmission which uses planetary gears. Gear selection is achieved by the electronic control of transmission fluid flow to operate various internal clutches. All right, and then it just gives us a little bit more information on how it works. Best test location is at the 19-pin connector or the 60-pin TCM connector, and then it gives us our connector views here for the solenoids. Let's see. Solenoids are calibrated from the factory and are not all the same. To replace a solenoid, match the replacement solenoid type, normally high or normally low, and the band number, more on that in a minute, with the original solenoid, or harsh erratic shifts, harsh shaft engagement, or damage to the transmission can occur. So if I don't put the right one in there, we will have a problem. And all solenoids except one may be serviced without removing the solenoid body. So I can actually service most of the solenoids without having to drop the valve body, which is nice. I do have to drain the pan. And diagnosis can be done with a scan tool viewing pin information on the CAN network for a desired component. We can see whether or not it's doing what it wants to do, or we can also test it as well. Like I said, I like testing. So in this case, we can do a resistance test, and that's the only test we have available. And then we would hook the red wire to solenoid power, and then blue wire to whichever one we have there. And I'll measure the resistance for each of the solenoids. Key off, each solenoid resistance should be about 4.8 to 5.4 ohms. If it's half an ohm, we got a problem. If it's 20 ohms, we got a problem. If it's 6 ohms, we got a problem. 4 ohms, we got a problem. All right, so we need to make sure it's within that operating range of the solenoids. If not, then we have a problem. So let's just say I have a problem. One of the solenoids giving me a problem, and I need to figure it out. So I've tested it without opening up the transmission. I also need to order a part. So I've already tested it. I know the resistance is bad. So the next step is going to be to order the part. Well, maybe it's going to take a couple days to get that part in. So there's a couple things we can do. So let's go into service resets and relearns. Going to be our quick link to all the resets and relearns. Going to go down to transmission, and it says reset or relearn transmission valve. Now this has different functional resets and calibrations. All right, so we have our different solenoids. We can turn them on and off. Gear commands. It also has transmission characterization and solenoid identification. We'll talk more about that one in a second, because that's what we're going to do. Let's go into repair information. Pop into shop key. Actually, I was in here earlier. So in shop key, we look at the solenoid information, and it has right here a picture of the solenoid, and it has a band number. Now, under normal circumstances, without a scan tool, I would have to drop the valve, drop the cover, anyways, drop the pan, and find this solenoid, whichever one it happens to be, out of the 7 that are on this transmission, and then ID which band number it has. Now, hopefully you get the right one when you're looking. Hopefully you know which one it is. If the third one or the fourth one, I'm not really sure. But hopefully you know. And if you figure it out, you can manually look. Or a nice thing that Ford has allowed us to do is we have that transmission characterization and solenoid identity. So if I go in there, there's 2 different things that we can do, 2 different tests. Cycle the key on. Transmission characterization is first. So this function is used to read the transmission strategy and identification from the module. Refer to vehicle workshop information for more. And this will tell us what kind of transmission it is. So it's a 6R140, as we saw. 13-digit solenoid body strategy, 8-digit solenoid identification. Yep, sounds good to me. And then it'll go and tell us the transmission strategy and the identification. They should match the service tag on the transmission. If the tag on the transmission is missing, damage, or if the strategy or identification does not match, it may be necessary to remove the main control cover and obtain the identification and strategy information from the solenoid body directly. But if that matches what's on the tag, then I know I'm in good shape. Then we have the solenoid band. So this is how we can read what band is in there, what solenoid, identify the solenoid without having to drain the fluid, drop in the pan, and disabling the vehicle for whatever period of time it's going to take to get that solenoid. So this function is used to obtain the transmission solenoid band information for ordering individual replacement solenoids. Refer to the vehicle workshop manual for more. Function is not supported for all transmissions, but in this case it is. For the following is a 6R140. Yep, sounds good to me. That's what we found in the other test there. And let's see. This function will provide transmission solenoid band information for individual solenoid replacement, solenoid body strategy, or identification will be required to obtain the solenoid bands. Function can be obtained from the module or the transmission service. We hit continue, and it's going to read it out. There's the strategy. We saw that already. And then there are my different solenoids. So let's say it's my solenoid B that I needed. It's normally high. There's my base, there's my element, and there's my band number. So I see that band number 4 on it. So with that, knowing all that, I could call up the dealership and say, okay, I need a normally high with this, this, and this. And you'll know you'll get the right solenoid. So you don't have to drop the pan. You don't have to find the band number. You don't have to figure out which one is which. And like I said, if it could take a couple of days to get one of these in, so I'd imagine maybe they have them just sitting on the shelf, but I'd imagine they probably don't. So you would need to order them, and then of course they'd come in later. So you'd have to pull the truck outside at that point and wait for the part to come at that point. So that's kind of a handy dandy little feature. I really like that one. And then if we back out of that, once we've done the repairs, we also saw that there is a reset transmission adaptives down here. So once I've done a repair, it's going to shift a little bit differently. Could have harsh shifts, could have some problems if I don't adapt or reset my adaptive. So we can halt the adaptive learning. We can resume the adaptive learning. We can stop use of the transmission adaptive, and we can clear it. So all you have to do to hit clear is just hit clear. Okay, this function clears adapt tables using the transmission. Key on, engine off, transmission and park. Hit continue, and we're done. Trans adapt tables are cleared. Hit exit, and then we're good to go. We're back to factory specs, and then it'll relearn as we drive, and good to go in that case. Many different schemes as to how manufacturers do this. All of them use something different. So just do your reading, do your research, but you do definitely have a lot of capabilities with scan tools and testing.
And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.